Hi everybody. Hope you had a great spring break. Been a good week off, although we've been off for a while, it feels like. But nice to kind of get back into the swing of things and get some more math done and out of the way. Hard to believe that it is almost May for you guys in your senior year and you're almost done. All right, anyways, the past couple weeks when you have been at home, you've been working on U substitution in order to integrate. That's still going to come into play, but really at this point, what would have happened if we were in school is we would have had our review and you would have had your test over all of integration, all finding area under the curve. So this week is really, again, not going to be anything overly new. This will be our last week before we move on to new stuff. But this is going to be kind of what your test review would have looked like. You're not taking a test, but kind of good practice for you to try and see if you remember all the different ways to integrate, some of the more basic ones. Also remembering that integration is nothing more than the area under a curve. And so we first learned to find area under the curve by drawing rectangles and using the limit of summations. So we're going to look at one of those problems again also. All right, let's jump right into it. I printed off 3 examples to work with you. First one here says find the area of the region under the curve of this parabola between 2 and 6. Remember, if you were finding area under a curve, it is really integration. That is what integration is. And so I'm going to find the area under the curve between 2 and 6 of this function. So the first thing I'm doing is really setting up my integral. This is a definite integral because I've got my values where I'm actually finding the area. Then I'm going to go ahead and, hey, there's no reason to do U substitution on this problem. I'm just going to integrate with the power rule. So the power rule says the integral of 9, that would be 9x, minus 1/4 times, well, the integral of x squared would be x cubed over 3. And eventually I'm going to integrate that between 2 and 6, but I'm going to clean this up a little bit and say that this is 9x minus 1/12 x cubed. Now that's what I'm going to integrate between 2 and 6. Remember, whenever you actually evaluate for bounds, you're going to plug in your upper one first. So this is going to be 9 times 6 minus 1/12 times 6 cubed. And then I'm going to subtract whatever I get when I plug in a 2. So 9 times 2 minus 1/12 times 2 cubed. All right. From there, now I need to clean this up. I should probably have grabbed my calculator, which I do not have in front of me. So 6 cubed, I'm going to just do this off the side real fast. 36 times 6, I think it's 216. Yep. So 216 over 12. Remember, you guys would be typing this into a calculator, no big deal. Minus 8 over 12. So, well, that would be, sorry, I'm trying to reduce these. 72 over 4. So I think I can divide by, let me do 216 divided, sorry. Again, you guys are going to be doing all this on a calculator, so I am sorry to kind of waste your time there. 72 over 4, which would reduce down to 1, so it's just 18. So this is exactly 18. So 54 minus 18 minus 18 plus, I'm going to reduce this. This is going to be 2/3. All right, so looking at this, well, 54 minus 18, 36. Why could I not do that in my head? No idea. I didn't need these when I distributed that anymore. That's going to be 18. Oh, you can't see any of this. 18 plus 2/3, which would be then 54 over 3 plus 2/3, and that would give me 56/3 for my final answer. I don't think that reduces. No, it doesn't. All right, so this is a bunch of scribbles and scratch work. some of that, a lot of that you could have done on a calculator very quickly. But remember, long story short, finding the area of the region under a curve is really just doing the integration of that. Integration is finding area under the curve. Okay, that's the first problem, and I will scan these all in. By the way, I found a really cool way to use your iPhone and take pictures of things, and they turn into PDFs. If you're interested in it, you're just going to go to the notes section of your iPhone, and in the notes section, you're going to click on the camera to take a picture, and it says scan as upload documents, and really it takes pictures of everything and then it turns them into a PDF. So that's a nice way if you want to try and submit pictures that way instead in a Google Classroom or anything. All right, evaluating the integral here. I threw in another trig one because I think you guys always like practice with trig. That's the thing you struggle with the most. So evaluating this one, notice this is an indefinite integral, so do not forget to add your plus c at the end. But when I look at this and I think about rewriting this, I would write this as 1 minus cosine theta to the negative 1/2 power times the sine of theta. This is definitely a problem to me where I cannot get rid of this exponent, so u substitution is going to be necessary. And so I'm going to say, hey, my inner function that I'm going to let u equal, I'm going to let u equal 1 minus cosine of theta. That's going to take care of this part. So that's going to be u to the negative 1/2. But then I'm trying to get rid of sine theta d theta and turn it all into u's. So I'm going to do that by taking the derivative over here. The derivative of u in terms of theta, well, the derivative of 1 is nothing, minus the derivative of cosine, remember, is sine, negative sine. All right, and then that would give me a positive when I do that. So du is really equal to the sine of theta. Bring over your, there you go, differential. And so this whole thing just becomes du. And now I'm really able to integrate a much easier problem using my power rule. Add 1 to the exponent, where the new exponent will be positive 1/2. And instead of dividing by 1/2, I'm going to multiply by the reciprocal, which is 2. I would add plus c and be done, except my final answer needs to go back to what it was. And it needs to go back to being in terms of theta. So this is 2 times 1 minus cosine theta to the 1/2 plus c. Leave it that way, no need to put the square root actually back into the problem. Okay, actually that trig one is probably easier than the first one. The last one, the one that is definitely going to take the longest to go over. This is going back to, hey, we're really finding the area under the curve of this quadratic. Again, remember, yes, we now know that area under the curve, or we should know that area under the curve is just integrals, and we really could do the integral of 5 minus x squared with my bounds, except I want to understand and realize that, hey, the limit process is an option as well. And so when we were doing this limit process, we thought about, I'm going to find the sum of areas of rectangles. And hey, the more rectangles that we made, the better. And so eventually we wanted an infinite amount of rectangles. So we were finding for an infinite amount of rectangles, the summation from I equals 1 to n being an infinite amount, of the area of the rectangles. And remember, area of the rectangles is base times height, which then we said we could go further with, and we could write that, oh, hi Parker.
Hi.
He's watching Star Wars right now in the background, so hopefully you don't hear it. Which one is this, Parker? It's the third episode one. It's when Darth Vader becomes Darth Vader, so he's pretty excited about that. All right, anyways, a lot of you don't care. Back to this. So again, we're finding area of the rectangles, base times height. The base of each rectangle of equal width, remember we called delta x. The height of each rectangle was found by doing f of x sub I, or the y value at some given x value. That leads us really to the two things you need to find. Two things to find would be delta x and x sub I. There were some formulas that we had back in the day for that. Delta x was found by doing b minus a over n, and x sub I was found by doing a plus I delta x. And then for our problem, actually determining these things, we would say 1 minus -2 over n would be 3 over n. And for our x sub I, that would be -2 plus 3i over n. I'm going to clean that up even further. There's a couple different options you can have with that, but I'm going to make this one big term with the denominator of n, and think about this as -2n plus 3i. Might be easier when I plug it back in. So now actually plugging this in, the area is going to be found by drawing an infinite amount of rectangles and summing up their area, where delta x is 3 over n, and f of x sub I is the function of 5 minus x squared in terms of x sub I, where we just found that x sub I is -2n plus 3i over n. All we need to do, which is going to take us a long time to do, is to clean this up at this point. And remember, when we did this, there were a lot of different ways you could go about cleaning this up. It's kind of your preference there. I'm going to just keep everything in the summation at the moment. This isn't necessarily right or wrong, it's just what I choose to do. I'm going to FOIL this out. If I FOIL that out, it is going to be 4n squared minus 12in plus 9i squared all over n squared. And then again, you have a couple different options for how you can go about doing this. I'm going to make this a common denominator and think about this as 5n squared over n squared. If I do this, oh, my kids are coming downstairs. Sorry, it might get a little chaotic here. If I clean this up in here, this would be 1n squared minus, I'm going to say plus when I distribute this negative to everything, plus 12in minus 9i squared over n squared, because I was able to combine these, by the way. I'm going to distribute these in to go a little bit further. This is just cleaning up. This is your basic PEMDAS rules. 3n squared plus 36in minus 27i squared. Remember, we are working with summations when we solve this way. This is not integrals. A lot of the same rules, but we don't need to have any dx or anything like that at the end here because it's a summation rather than an integral. And then I'm going to go ahead, I'm going to reduce all of this. Hold on, I feel like I lost something along the way. I'm coming, don't go anywhere, sorry. Quick timeout. Nope, so far so good. Okay, say hi to them. The kids I'm talking to on my phone.
Hi.
All right. Our goal with summations is to get rid of this and to make it look like one of our common summations. Remember, we had the summation of a constant, we had the summation of I squared, or the summation of I cubed. Okay, that doesn't look like that yet, so we need to do a lot more reducing. I'm going to now break these up and write them into more simplified fractions. This one here, if I did it, would be 3 over n plus 36i over n squared minus 27i squared over n cubed. I can then break these up into separate summations. Remember, that is what our properties allow us to do with that. And when I think about it that way, Now I have the summation of a constant, which we'll deal with in a second. Plus, well, I can remove my coefficient and just have the summation of I. Same thing on this last one. I can pull out the 27 over n cubed and just have the summation of I squared. That leads me to having, Case, I need you to leave for a second, buddy. Okay, I'll be over in a sec. Sorry, bud. All right, so I've got my common summations here. I can apply the properties formulas here. I can even do it to this one as well, because remember, that's a constant. I have not done anything with the limit yet. That the summation of a constant is that constant times n plus 36. The summation of I, these would always have been provided for you, or n times n plus 1 over 2. And the summation of I squared is n times n plus 1 times 2n plus 1 all over 6. So that's going to, let me grab one more piece of paper, hold on. All right. Last things we need to do is clean these up and we can evaluate our limit. Remember, to evaluate a limit, the easiest way to do it, if we can, that's an approaching y value, is just plug in. But I can't plug in with the way that it is now, so I reduce things. I clean them up. That's going to become a 3. If I reduce this one, I'm going to get 18 times n plus 1 over n, minus, reducing this is going to be 9 times 2n squared plus 3n plus 1 over 2n squared. And I still can't plug in because I'm going to get our indeterminate form of infinity over infinity, so we keep going. Cleaning this up even more. Well, hey, I'm just going to break these apart into separate fractions, which will allow me to eventually determine the limit. I'm going to do 18n over n plus 18 over n. We get to there. Reducing these. We're almost done. Remember, this was the long way you guys hated. And you said there was tons of room for mistakes, which is true. You just got to take your time. You got a lot of time now at home, right? Hey, make up some of these. You can find a million of these problems to do online if you want. All right, you don't want to do that. Last step on this problem is to actually go ahead and evaluate the limit by plugging in. And anytime I plug in and I end up with a constant over infinity, those terms become 0. And I'm left with 21 minus 9. The area is 12 units squared. Long way to get the answer, but it was our first way, and it's important to look back and understand that as well. Okay, so I've given you 3 different examples of problems you would have seen on your test. I'm going to give you the test review. I ask you to please do that. Make sure you check the answer key that I'll upload to Classroom as well. Reach out with any questions you have. I miss you guys. I hope you're doing well. Hang in there. Stay healthy.